So our goal in this problem is to sketch a graph of f of x equals natural log of x to the fourth plus 27 using all of the algebra and calculus knowledge that we have so far. And we're going to try to do this without using the graphing capabilities of our graphing calculators. So let's start with domain. Remember that when we are looking at any log function, whether it's a logarithm base 10 or in this case a logarithm base e, we want to look at the argument. And so the argument here is x to the fourth plus 27, and the argument cannot be 0 and it also cannot be negative. So that means that x to the fourth plus 27 must be greater than 0. But notice, no matter what value you plug in here for x, when it gets raised to the fourth power, it's always positive. So that means that this expression will always be a positive number. So therefore our domain is all real numbers. Now before you move on to the intercepts, think about the domain because this will also give you some other useful information on this list. If the domain is all real numbers, then that means that you don't have any discontinuities in the graph. So that would tell us then that we don't have any vertical asymptotes. So down here for vertical asymptotes, we can say that there are none. So let's move on to the x-intercept. So anytime we're finding an x-intercept for any type of function, remember that's always where the graph crosses the x-axis, so we're going to let y equal 0. So 0 is equal to the natural log of x to the fourth plus 27. This is a log equation that we're going to try to solve. So remember that natural log is really a logarithm with a base of e. So we want to think of this log equation in its exponential form. So if you rewrite it, this becomes e to the 0 power is equal to x to the fourth plus 27. Coming over here, e to the 0 power is 1. So we'll solve this equation. 1 equals x to the fourth plus 27. Subtracting 27 from both sides, we're going to be left with negative 26 equals x to the fourth. But we'll quickly realize that when we go to take the fourth root of both sides, we're not going to be able to do that because we'll end up with some imaginary numbers, not real numbers. So that tells you basically there's no solution to this equation, which means over here back to the x-intercepts, there are none. So we know that there are not going to be any x-intercepts. The curve is not going to cross the x-axis. So now we'll move on to finding the y-intercept. So the y-intercept is going to be found by letting the x value equal 0. So we're finding f of 0, which would be the natural log of 0 to the fourth power plus 27. So that's going to be the natural log of 27, which we'll definitely need to use our calculators to estimate that value, and that's about 3.3. So either you can list the y-intercept as just 3.3, or you can list it as a coordinate. When x was equal to 0, the y value was approximately 3.3. I like to go ahead and leave it in its decimal form because we actually want to sketch a graph, so we want to plot this point. And I'd recommend that you start building your graph right now that we actually have a point on the graph. So go ahead and plot that y-intercept of 0, 3.3. Next, we'll move on to the horizontal asymptote. So if there's a horizontal asymptote, remember that that is going to impact the far right and the far left of the graph, which means we have to compute a limit as x approaches infinity of this function. Natural log of x to the fourth plus 27. Sorry, let me rewrite that. Natural log of the quantity x to the fourth plus 27. So there's not any special algebra to be shown here. We just have to think about the behavior as x becomes a really, really large number. So if x is infinitely large, x to the fourth is also infinitely large. And therefore we're taking the natural log of an infinitely large number, which you can verify that if you need to on your calculator, that when you do the natural log of larger and larger and larger numbers, the output is also getting larger, larger, and larger. You could also confirm this thinking about the graph of the natural log curve. If you analyze the graph of natural log of x, it would look something like this. So you can see on the graph that as we go to the right, as x is becoming infinitely large, the y values are also growing. They're not growing very quickly, but they are growing. So therefore, the value of this limit is infinity. So what this tells us, the right behavior, as x goes to infinity, the y values are also going to infinity, which tells us that there's not going to be a horizontal asymptote as x goes to positive infinity. Now, it is going to be necessary to go ahead and think about the other side of the graph, which would be as x goes to negative infinity. So let's see if this limit would change if x is approaching negative infinity. So again, thinking about a really, really negative number, we're taking a negative number and we're raising it to the fourth power, which is going to turn it into a very large positive number. So even as x goes to negative infinity, my y values are still going to get infinitely large. So again, this is going to confirm that we do not have a horizontal asymptote either. So I just looked at my list and I realized that I neglected to put symmetry on my list. So I apologize. Let's go back for a second and talk about symmetry. I actually usually do symmetry before we get to the asymptotes, because sometimes the symmetry can give us some good information about the asymptotes as well. So testing for symmetry, we're going to substitute in negative x into this function to look at the output. So we're going to substitute into our natural log. That would be negative x raised to the fourth power plus 27. But a negative value raised to the fourth power is going to end up being positive. So this is equivalent to natural log of x to the fourth plus 27. So what I'm getting here is the same function as the original function. And anytime you substitute in a negative x value and what you get out is the same as the original function, that tells you that your graph has y-axis symmetry. So we do have symmetry on this function. It's going to be y-axis. And if I take a look at the work that we just completed for the horizontal asymptotes, that should make sense because we found that the limit as x went to positive infinity was the same as the limit when x went to negative infinity, which would make sense if the graph has y-axis symmetry. So if you find your symmetry first, then that will save you some time because you won't actually have to compute the limit as x goes to negative infinity. You would only have to compute the limit as x went to positive infinity. So now we'll move on to figuring out where this function is increasing and decreasing, and then hopefully find any local maximums or minimums. So for increasing and decreasing, we want to take a look at the slope of the graph, which means we're going to analyze the derivative. So taking the first derivative, we notice that this function is composite. So we're going to look at the derivative of the outer function. And if you need to see those pieces, you can think of it like this. The outer function is the natural log of some quantity, and the inner function is x to the fourth plus 27. So when we take the derivative of the outer function, derivative of natural log of something is going to be 1 over that quantity, and then we will chain on the derivative of the inner function, which is the 4x cubed, the derivative of x to the fourth plus 27. So using the chain rule, the f prime would look like 1 over x to the fourth plus 27, and then we would chain on with multiplication, multiply by 4x cubed. So in other words, we'll end up with 4x cubed divided by x to the fourth plus 27. So we'll use this form of our derivative to find our critical numbers. Now, critical numbers are found by analyzing where the derivative is equal to 0 and where the derivative might be undefined. So in order for this derivative to equal 0, since it is a fraction, we know that a fraction would only equal 0 if the numerator is equal to 0. So we can basically just set the numerator equal to 0 and solve. 4x cubed equals 0. So clearly x equals 0. And then in order for this fraction to be undefined, that would occur when the denominator is equal to 0. But we already discussed this with the domain of the function. This won't ever happen. We can't have a 0 here. You could actually subtract 27 and take the fourth root of both sides, but you wouldn't be able to do that in the real number system. So this doesn't ever happen. So this is a never. So the fact that the derivative is never undefined tells us basically three things. There are no corners on this graph, there are no discontinuities, and there are no vertical tangents. So right now I'm getting one value of x equals 0. Now remember, this is only a critical number if it is in the domain of the function, but since the domain of the function was all real numbers, then this would be our critical number. So this is a place where the derivative might change sign. So we need to analyze the first derivative around 0 to see if we indeed do have a change in sign, which will then tell us whether we have a maximum or possibly a minimum. So we're going to test values smaller than 0, maybe -1, and larger than 0. And remember, you're testing into the derivative. We want to know the sign of the first derivative. So we're going to substitute -1 into the derivative. That would be like computing f prime of -1, which you certainly don't have to write down on paper. You could do that in your head if you wanted to. In fact, this one's not too bad because if you just think about the division, the denominator here is always positive. So looking at this in fraction form, it's like we're always going to have a positive number here in the denominator. So we really only have to analyze the numerator, the 4x cubed. So if we substitute a negative number into 4x cubed, we're cubing a negative number, that result is definitely going to stay negative. And a negative divided by a positive results in a negative. Same thing, we want to substitute +1 into the derivative. Once again, the denominator is always going to be positive, and if you substitute +1 into the numerator, it is also positive. So the derivative does change sign. The derivative goes from negative to positive. Now remember, this negative sign represents the slope. So if the slope is negative, that means the function is decreasing. And then if the slope changes to positive, then the function increases, which means that we've reached a point here where we have a local minimum. So we have a minimum at 0, and we also can answer that we know that the function is decreasing from -infinity to 0 and increasing from 0 to infinity. So I'll go back and fill that in on our original screen. So once we've filled in the intervals where the graph is increasing and decreasing, we've decided that there is a minimum at 0. We do need to find this y value. This is actually a coordinate on the graph, so we need to substitute 0 into the original curve. So that's going to be the natural log of 0 to the 4th power plus 27, which tells me the natural log of 27 is going to be the y value. And notice we actually did that earlier. That was a y value of 3.3. That was our y-intercept. So it turns out that our minimum is going to occur at the y-intercept. So I would now go to your graph, and I would make a little note to yourself that this is a minimum occurring at 0, 3.3. And we also know that there is no max, so you can say none for the maximum. That's it for the first derivative, so now we can move on to the second derivative. So to find the second derivative, we're going to need to apply the quotient rule. So our little saying for the quotient rule, to help us remember it, is low d high minus high d low, all divided by low squared. So low is going to be the function in the denominator, x to the 4th plus 27, times the derivative of the numerator, So that's low d high, derivative of the high, which is going to be 12x squared, low d high, minus high, the numerator function or expression, 4x cubed. D low is the derivative of the denominator, which is also 4x cubed, all divided by the denominator squared. So that's our quotient rule. I'm going to clean that up a bit. Not too much. All I'm going to do pretty much is bring this 12x to the second and just rewrite it out here in front, and then multiply the 4x cubed times the 4x cubed. So I have 12x squared times the quantity x to the fourth plus 27 minus 16 x to the sixth, all divided by x to the fourth plus 27, the quantity squared. Now at this point you have two options. You could distribute the 12x squared, or you could choose to factor at this point. And I try to encourage my students to work towards factoring, because that's going to be probably the most used method on some of the more complicated functions. So I've underlined in red, these are our two terms that we're going to want to factor. We want to find the greatest common factor between these two terms. So between 12 and 16, we can factor out a 4. And between the x squared and the x to the sixth, we could factor out an x squared. So that's my GCF, my greatest common factor. And I'm going to be factoring that out of this first term here, as well as this second term. So factoring out a 4x squared is going to leave me with a 3 times the quantity x to the fourth plus 27. And then the second term, the 16x to the sixth, once we factor out 4x squared, will leave us with a 4x to the fourth power. Still all divided by x to the fourth plus 27 raised to the second power. So now what I have in red in the brackets, we want to simplify. So we'll go ahead and distribute the 3. Remember, at any time, pause the video, maybe get a couple steps ahead if possible. Then you can resume and check your work. So 3x to the fourth plus, let's see, 27 times 3 is going to be 81. Minus 4x to the fourth, all divided by x to the fourth plus 27, the quantity squared. So it looks like my simplified second derivative right now. I have 4x squared times 81 minus x to the fourth, all divided by x to the fourth plus 27, the quantity squared. Now the second derivative is going to give us an idea about concavity. So we want to figure out where the second derivative changes sign. So we know that it can change sign at a point where it is equal to 0, one of the zeros, and it also might change sign at a point where it is undefined. So to set this second derivative equal to 0, we would set the numerator equal to 0. And it's already factored, which is nice, so that work has been done already. And we need to solve this equation. So since it's already, again, here in factored form, and that's multiplication, we're just going to set each of these factors equal to 0 and solve. So divide by 4, square root both sides, and we have x is equal to 0. Here, if I add x to the fourth, I have 81 is equal to x to the fourth. So if I take the fourth root of both sides, I'm going to end up with x is equal to both positive and negative 3. That works out pretty nicely because it's the fourth root of 81, which is a nice whole number. Where's the second derivative undefined? Again, that would happen when the denominator is equal to 0. But we've already attacked this a few times. This doesn't happen because the denominator is always positive, so that's never. So right now we have 0 and plus or minus 3, and we're going to want to test around those 3 values. So we'll test a value smaller than -3, maybe -4, between -3 and 0, between 0 and 3, and bigger than 3. You can test in your calculator, but a lot of times I find it actually faster not to use your calculator, because remember, the denominator here, no matter what I substitute in for x, I'm always going to get a positive in the denominator. And then 4x squared, no matter what I substitute in there, will also be positive, which tells you really you only have to analyze the 81 minus x to the fourth to figure out the sign here, because everything else is going to be positive. So for example, when we substitute -4, we're plugging -4 essentially into our second derivative. So it's f double prime of -4. So if we go 81 minus -4 to the fourth power and compute that, we notice that we're going to end up with a negative number. So a positive times a negative, all divided by a positive, results in overall a negative. So now we test, let's see, we test -1 maybe, and we'll substitute -1 into the second derivative. So really looking at 81 minus -1 to the fourth power. And that's definitely going to give us a positive. Now, if you remember, we said we had symmetry. We have specifically y-axis symmetry. So if we have y-axis symmetry, then between 0 and 3, here I should have the same concavity that I have here between -3 and 0. And if you actually check that, in other words, if you substitute 1 into the second derivative, 81 minus 1 to the fourth power, and you notice that's definitely positive. So sure enough, we do have a positive there, as we should. Which means I could go ahead and fill in that my next sign should be a negative without actually doing the testing and the substituting. So these signs are telling me about the concavity of my graph. So this negative tells me, the first negative here tells me the graph is concave down. Then the graph changes to concave up, which means I have an inflection point at -3 because the concavity changes. However, at 0, the concavity goes from concave up and it stays concave up, so that means there is no inflection point at 0, but rather there is one here at 3 when it changes again from concave up to concave down. So we do have 2 inflection points. So now let's take this second derivative sign chart and we can go back to our original screen and we can fill in our intervals for concavity. So the graph begins, let's see, concave down. So we're going to be concave down on the x interval -infinity to -3. Then, oops, sorry about that. I put that in the concave up spot. Let me go back. We're concave down from -infinity to -3. Then the graph goes to concave up from -3 to +3. And then we're concave down again from 3 to infinity. So there's actually 2 intervals where the graph is concave down. So our inflection points occurred at -3 and at +3. So the last thing we need to do is find the y values of our inflection points. And these are points on the original curve, so we're going to actually substitute these values, these x values, into the original function. So we're going to find f of 3. So that would be the natural log of 3 to the fourth power plus 27, which is definitely going to be something you'll put in your calculator. That's the natural log of 108, which I'm getting to be about 4.7. And remember, the y value would be the same when we put in -3 because we have y-axis symmetry. So the inflection points are at -3, 4.7, and +3, 4.7, which now lets us graph those points on our graph. So +3 and -3, 4.7. and I like to mark them as little IPs. So we've found all of the pieces and we're finally there, 25 minutes later, ready to try to sketch everything. So I go from left to right. I start on the far left-hand side of the graph. So I would begin looking at my concavity. So back to my original screen here. The graph started off concave down, and then it also starts off here decreasing. So concave down and decreasing. So going back to my graphing curve, I'm concave down and decreasing. That would be something like that, concave down and decreasing. Then I change to concave up at the inflection point, and I'm going to be concave up until I hit that minimum, and then I stay concave up all the way to my other inflection point. And then remember, it has y-axis symmetry, so I would have a nice mirror image on this right-hand side. So that means it changes to concave down, but it continues to increase. And the domain is all real numbers. We don't have any horizontal asymptotes. We don't have any vertical asymptotes. It looks pretty good. And at this point, finally, I would go, all right, let me go to my graphing calculator, substitute, or rather put this function into my graphing calculator and see how well we did. How good is our rough sketch? You survived. These take a lot of practice, for sure. So take your time, go one step at a time, and see if you can put all the puzzle pieces together, but this is our end goal, a decent sketch using all the algebra and the calculus that we've studied so far.